How's everybody doing? Bet we can hardly wait for a break next week. I know that that's the way I feel. All right, good to see you tonight. We're going to continue our discussion about functions. We've been thinking about functions as sets of ordered pairs, and we're going to change our point of view very slightly tonight. We'll continue looking at them as ordered pairs, and we've got our arrow diagrams that are helpful. But there's another way to look at a function as a machine with input and output. And that can be particularly helpful when we're looking at composing functions. I think it gives a good visual of what happens during function composition. So that's what we're going to be looking at tonight. I'll write our goals for you here. Let me go ahead and pin this. So our goals are to continue with functions. Don't forget the worksheet on chapter 7, since we won't have time for me to grade anything from chapter 7. So we'll continue with functions. Let's make sure this is in focus. That's a little better. We're going to ask, what does it mean for two functions to be equal? There is one WebAssign problem that asks you if a couple of functions are equal, so we'll talk about that. And then, of course, in section 7.3, it's about composing functions or function composition. You probably did this in high school, and certainly if you've taken Calc 1, you've done function composition, because when we use the chain rule, we have to decompose functions into, two functions that get composed. But we'll do a little machine approach, which is a really nice visual that can help you figure out, hey, what's going into where. And we'll continue, of course, with arrow diagrams. And then we're going to ask and answer this important question: when does a function have a functional inverse? We've looked at inverse images of function subsets, but that's not the same as having a functional inverse, a function that actually undoes the action of another function. That would be its inverse. And we'll look at a particular important function called the identity function. Okay. Are there any questions at all about procedures or just, what's going to be covered on the test? It's chapter 5 material, chapter 6.1, and chapter 7 material that we will be finishing up tonight. And that's on the reading page. It's been listed on the reading page for a while. Anybody got any comments? Let's see, we got a chat. Let me open the chat. That must be Ronnie. Thank you. I'm okay. I'm okay. Just trying to stay organized and just trying to keep up. Trying to keep up with the workload. All right. So let's do a do now together, just to kind of warm up and think about functions. So here are two sets. We're going to let X be the set containing little a, little b, little c, little d, and little e. And we're going to let Y be the set containing little x, little y, little w, v, and t. Consider this subset of x cross y. Okay, we'll call it F. And of course, the question is going to be, is F a function? Here we go. It's a set, of course. First ordered pair is little a comma little x. Second ordered pair, little b comma little x. Third ordered pair, little c comma little x. Fourth ordered pair, little d, x. And last ordered pair, little e, comma x. Is f a function from x to y? So this gives us an opportunity to review the definition of a function. Shall I state the definition of a function? Does anybody want to hear it? Okay, I got a little nod from Eric. Thanks, Eric. It's good to see you. It says each element of the domain, which would be x, maps to exactly one element from the codomain. So if we're thinking arrows, each element of the domain has exactly one arrow coming from that element and pointing to an element of the codomain. The key thing is every element of the domain has to map or pair with an element of the codomain, but it can only have one partner from the codomain. Okay, did that help? Thanks. So what do you think about this set of ordered pairs? It is a subset of x cross y, so it's a candidate for a function. We just have to wonder if it satisfies the definition. What do you think, Danny? Do you think it does? I got a nod from Eric. I got a vote of yes from Eric. What do you think, Nick? Nick, you thinking yeah? Yeah, I got a thumbs up. Kendall, got any ideas about this one? Edwin, any idea? Any thoughts?
I agree.
Thank you. So, folks, you see, tried to fool you, but I couldn't do it. It doesn't matter that every single domain element, A, B, C, D, E, maps to X. That's fine. The point is, each element of the domain got paired with exactly one element of the codomain. Okay? Doesn't matter which one. It doesn't matter which codomain element they pair with. They just have to pair with exactly one. So it's not a one-to-one function, okay? It breaks the one-to-one property about as badly as it possibly could. But the solution is yes. And if we wanted to write one sentence to explain why we think it's a function, could you do that? Take 30 seconds and write a short sentence to justify that it is a function, because you're going to have to do this on test 3. You're going to have to write some justification sentences. It's good to get a little practice. So something that tells us every element of the domain has exactly one partner from the codomain. Notice, though, we could make just a comment. F is not one-to-one. That's sort of the most obvious thing about F, because, well, F of A is equal to X, and that's equal to F of B, but A is not equal to B. Is F onto, by the way? So this is a good opportunity for us to review the definitions of one-to-one and onto.
F isn't onto Y
Yeah, it's not onto Y. And why is that, Edwin?
because it doesn't, F doesn't have every element of Y present in that set.
That's right. Well, as a second coordinate, right. Each element of Y would need to appear as one of these second coordinates. In other words, the arrows that shoot into Y is like the target, the codomain is the target. Those arrows would have to hit each and every one of those elements at least once for F to be onto. And they don't hit Y or W or V or T, right? So if you drew a picture, it's about as far away from being onto as it could be. Questions? Okay, good. I hope you feel, kind of warmed up and in a function mood. Let's talk about what it means for two functions to be equal. By the way, does anybody want to read their statement to us just so we can hear it? Does anybody want to have their statement checked of why the function is a function?
Well, I said that F is a function from X to Y because every element in X has exactly one pair with the codomain Y.
Okay, close enough. I'd accept that.
I said something similar to yours, but I said at least one instead of exactly one.
Oh, you can't say at least one because what would happen if A went to X, but also A, let's say this was A, let's say it also mapped to Y.
Mm.
So then it would have at least one partner in Y, but it would have too many.
Okay.
So at least one is bad. It's got to have exactly one. Does that make sense?
Yeah.
Yeah, and if you look at the worksheet, you'll see something going on with that. Yeah, one element from the domain cannot have two different arrows going to two different codomain elements, okay? So please do review day 22 notes just to make sure you've sorted that out, okay? Good. Anybody else? So think about what do you think set equality would mean? Let's look at the gallery. Like our natural notion of what it means for any kind of mathematical object to be equal to another mathematical object. What do you think it's going to take for two functions to be equal? Just from your intuition.
They have like the same set.
They have to be the same set of elements. That's a big part of it. That's a big part of it. Anybody got anything else that they want to add or think we should add if we're trying to figure out what it means or what it means to say two functions are equal? Okay, I'm going to write the first line of this definition of set equality. And before I write any more, maybe just from what I write here, you might have some more ideas because I want to remind you what goes into the definition of a function. Given functions, say f from A to B and g from C to D, we say f is equal to g. That's what we're defining. And of course, it's denoted by exactly what you think it should look like. It's F equals G. Oh, let me pin this again. If, okay, just based on what you see here, and certainly Edwin's got the bulk of it, they have to have the same ordered pairs. But can you see anything else that might come into play here based on, the what goes into the structure that we call a function? If you go back to the definition of function, the very first phrase in that definition is that we have two non-empty sets, X and Y, right? Without the sets, we can't build the function because the function is a subset of a cross product of two non-empty sets, right? So what else might we need in order to nail function equality? Well, I'll tell you. The domains have to be equal. And the part that isn't necessarily that apparent is that the codomains actually have to be equal. I don't need an equal sign here. So A needs to equal C and B needs to equal D. And kind of what we consider kind of the meat of the matter, right? The main course is what Edwin said. F and G have exactly the same elements. I.e. the same ordered pairs. Because that's what the elements look like. They're ordered pairs. It's not as obvious unless we look at an example. Remember our motivating example from last time, and it was f of x equals x squared. And it was kind of a nice little example because it allowed us to think about, what it means for a function to not be one-to-one. It also let us talk a little bit about, the graph of a function. And it's an equation function, and it's also a function on an infinite domain. We've been playing lots of finite domain games. But there's a difference between f mapping from the reals to the reals versus g of x equals x squared, where g is mapping from the reals to the non-negative reals, which is the reals minus the negative reals. You see, f is not an onto function because none of these negative real, these are the y values, they're the f of x values, these are the x values, the first coordinate values. None of these negative y's become second coordinates because when you square a real number, the square is not negative. We know that it's never negative. So this function with the domain reals and the codomain reals is not onto because none of these negative codomain values ever get hit, right? But G, same equation, G of x equals x squared, where we're mapping from the reals to the non-negative reals, the reals minus the negative reals. Well, this part of the y-axis is no longer part of the codomain. So G is onto. Does that make sense? So even though they have exactly the same ordered pairs, one is onto, one is not. So that's all I wanted to say there. And there's a machine idea of a function. So, F and G, I'll just say, have the same ordered pairs. But the codomains are not the same. F is not onto. G is onto. So F is not equal to G. Okay. Just wanted to make, it's no big deal. I just thought it was a point worth making. So I'd like to draw a kind of different image that views a function as an input-output machine. Okay, so here's the machine idea of a function. I think you'll like it because it's very intuitive, especially when we start composing functions. Imagine that we have a function f, and I'm going to draw it like a little monkey grinder, okay? And what happens is we drop in an element x in the domain, whatever that domain is, right? And then, x drops into f and f grinds on x and makes that noise too, right? And out comes, well, the image of x under f, which we call, of course, f of x. And it's an element of actually the range of f, which is a subset of the codomain. So this is, a function f. And then for such a function, the ordered pair x, comma, f of x is exactly what the ordered pair, looks like. This will work for every function. This is true for any generic function. Okay, so why do I like the machine idea of a function? Well, there's an input and there's an output. And even if, let's say that we wanted to somehow build a function that had two outputs, but they were somehow connected. I'll give you an example. Let's say we want to input information about a divisor, D, and a dividend, A. So there would actually be two inputs. And then what we want to come out would be the Q, the quotient, and the remainder R, so that A equals DQ plus R. In other words, let's say we wanted to build some kind of a function or a computer program that would take as input A and D and give as output A div D, in other words, Q, and A mod D, in other words, the R. Okay. Well, to get that to be a function, we've got ways, okay? We've got methods. And what we do is we input the ordered pair A, comma D, and just call that one object. And then we would output, say, an ordered pair Q, comma R, and call that a single output. You see what I mean? So there are ways to fix it if you need to put in several pieces of data and get out, say, some kind of a set. In that case, the codomain is a set full of sets. And the domain could be a set of sets or a set of ordered pairs as well. So there are ways to fix it if the job that we need the function to do is, more complicated than just taking a single data input and spitting out a single data output, okay? Let's look at function composition. We're just trying to kind of get our heads around the basic ideas of functions. All right, so do you remember function composition? Let me see if I can recall with you. Definition. Given functions, we're going to have two. F from A to B and G from B to C. The composition of G by way of F. Now that's the long way to say it. The composition of G by way of F. We don't usually say it that long, but I'll write it because it tells a lot. Also called G of F, denoted by, and here's the notation, it's G with an open hole operator, F, okay, is defined as follows. Well, first of all, G of F is a function that starts in A and lands in C. The thing to understand about this weird notation is that even though we say G first, it's G by way of F. F actually acts first. F takes elements from A and maps them into B. Oh, well, G picks up there. G takes elements from B and maps them into C. So G of F, or G by way of F, takes elements from A and sends them all the way over to C. They make a pit stop in B along the way. And the technical definition is where G of F of X, and yes, we do put parentheses around G of F, is actually equal to G of F of X. In other words, you drop F of X into G, and that's what it acts on. Instead of just a plain old X, it's acting on F of X. So let me draw you this picture that I like so much of these stacked functions. It's like having a stacked appliance in some sense. Okay, so what happens? Well, we drop in an X from the domain of F. That's A. So an X from A gets dropped into F and it grinds on it. And out comes F of X. But it lives in B because the codomain of F is B. And that is exactly the domain of C. So the domain of G. So G can take this F of X from B and grind on it, and out will come G of F of X, which is what we're calling G of F of X. And this is an element of C. Does that make sense? Questions? Answers? Shall we play the game? Shall we do one? Let's play the game. Let's play the function composition game. But I think this visual makes it really easy to kind of see what's going on. And I've got a couple of other visuals that will help you with this. Okay, so we're going to play the function composition game. All right, here we go. Example 2. Let's give ourselves 3 sets, folks. We're going to let A be the set containing 1, 2, 3, 4, 5, 6, and 7. B is going to be the set containing little a, little b, all the way up to F. C, D, E, and F. And we're going to let set C be the set containing little x, little y, little z, little w, little t, u, and v. Okay. So we've got 3 sets. We're going to define F from A to B and G from B to C as follows. Okay. F is going to be this set of ordered pairs. Okay, it's a function, it's a set. All right, 1 goes to A, 2 also maps to A, 3 maps to B, 4 maps to C. That's a C, not an E. Looks like an E, but it's supposed to be a C. Let me clean that up. Okay, still not great, but I think you got the drift. 5 maps to D. 6 maps to E. And 7 maps to B. Okay, that's F. All right, now G. G is going to map from B to C. So its first coordinates are going to come from B. Its second coordinates will come from C. Here we go. G is going to be this set. Little a maps to little x. Little b maps to little y. Little c maps to little z. D maps to w. E maps to T, as in Tom, and F also maps to T. These are functions. I would not be using this notation unless they were functions. We don't use this notation when we're asking the question, is it a function? Okay, we only use this notation if it's established or clear that we're dealing with a function. Okay, so A. We're going to find G of F. And then we're going to answer a few questions like, what is its domain? Its codomain? What is its range? Or what is range of G of F using our range notation? So I'd like to give you kind of a nice, and we'll have a couple more questions at the end too. We know we're going to work on this for a while, but let's go ahead and answer at least these questions. And I'd like to show you a way to do this if you don't feel super comfortable with function composition. It's helpful to realize, from the beginning, what the domain and what the codomain are. So G of F acts first, and we know F maps from A to B. After F acts, then G acts. and G maps from B to C. So just like in the definition, G of F is going to map elements from A into elements from C. So we can kind of answer this first couple of questions about domain and range by just saying, hey, notice or note, G of F is a map from A to C, where obviously A is the domain and C is the codomain. So that's good to get that sorted at the beginning so that we start dropping the correct elements into G of F. We need to know what the domain is. And we'll be looking for them to pair with elements from C eventually. All right. Now we'll ask this question, what is the range of G of F? That'll be easier to answer once we see what the elements of G of F are. Let's do that now. So now, finding G of F, finding the ordered pairs. Okay. Well, we're going to look at x equals 1 because it's in A, and we're going to look at x equals 2 and x equals 3. In fact, we're going to look at all of the domain elements. I'm just going to line them up like this. You know how Dr. Good is. I like to kind of stay organized because I don't like to think too hard. And I find that organization of my notation can ease that burden of having to think really hard. And then once, we find the ordered pairs, then we'll write them. We'll write them here after we figure them out. All right, so this is the deal. 1 is going to map somewhere under F. And then wherever 1 goes under F, we'll leave some room, we're going to put that there. Then G is going to pick up from there and take whatever's here, that intermediate image, and map it somewhere. So let's do this. Where does 1 map to under F? In other words, what is F of 1, folks?
A.
Yeah, because 1 is paired with A. Right? So 1 maps to A. Okay, great. Now G is going to act on A and send it, A is living in B, right? G is going to send A here into C. Where does G map A, folks?
X.
Yeah. Is everybody on with the program? Is it super simple? Or are you following? Sometimes I don't know if people don't respond because they don't understand, or they don't respond because it's too easy. Okay, so we're going to do all of these. And you don't have to do this. I'm just doing this for your notes, and it can be a way to keep yourself organized as you work through a composition problem. But of course, you can also just say, hey, 1 goes to A and then A goes to X. So 1 goes to X. So our ordered pair that came out of this first process is that 1 maps to little x. See what I mean? All right, let's do the rest of them. You go ahead and work on those, and I will start filling this in. To make it look nice for the notes. All right, where did 2 go?
A
2 went to A under F. And then what happened?
goes to X.
Just like 1 did. So we have the ordered pair. Maybe I'll do these in black. 1 mapped to X, and so did 2. Yeah, it's a little easier to see. Somebody else. Where does 3 go under F?
B.
Good. And then what happens to B when G acts on it?
Y.
Great. And so what's our ordered pair that's going to go into G of F?
3Y.
Exactly. All right. Somebody else. Where's 4 go? Oh, Danny's saying C. Good. 4 does go to C. And then what happens? Thanks, Danny. Z. So 4 winds up going to Z. So I mean, it's easy to get the swing of it, right? 5 maps to D, and then D gets sent to W. 6 maps to E, and E goes to T. So 6, T. And 7 maps to B, and we already figured out that B maps to Y. So we have the ordered pair 7, comma Y. So that's just showing the work. And this is optional. You don't have to do this, okay? It's just supposed to help you out. So now, our solution continued because, here we already wrote what the domain and the codomain are. So G of F is a set of ordered pairs, 1, comma X, 2, comma X, 3, comma Y, 4, comma Z, 5, comma W, 6, comma T, and 7, comma Y. Dr. Good went a little bit buck wild with this one. I had a lot of domain elements, didn't I? What's the range of G of F? Shall we review the definition of range?
From X to T.
From X to T?
Yes.
X, Y, Z, W, T. Yeah, X, Y, Z, W, and T were all Y coordinates, second coordinates that actually appeared, So does everybody remember the range are the elements of the codomain? That's elements of the set C that actually appear as second coordinates. And yeah, X, Y, Z, W, and T all appeared. Okay, so the range, any questions on that? X, Y, Z, W, and T. All right, any questions? Well, let's just stick with this example. I'd like to show you how the arrow diagram can be drawn for this particular example. And then we'll ask some questions. Just to save time, okay? So you can think of kind of a double arrow diagram where you first draw the arrow diagram that shows what F does. Here, I'll put the definition of F and G up where you can see them. So you draw the arrow diagram for F, and then, here's B in the middle. So then you draw the arrow diagram for G. Notice both little e and little f map to T, right? And as you just like, you can follow this to figure out, oh, 1 goes to A, goes to X. 7 goes to B, goes to Y, and that sort of thing. All right, so that's G of F. That composition is G of F. Or you could draw G of F just like this, with A and C, without the middle, without what's going on in the middle. It's up to you. But now let's practice the image game and the inverse image game. All right. And we can look at these diagrams to try to answer that. In fact, we can probably just use the second diagram because it's more simple. Find each set. This is part B of this example 2. Find G of F of the set containing 1 and 2. So the image of the set containing 1 and 2 under G of F. This is great practice for the test. And then find G of F of the set containing 3 and 4. Then we'll find the inverse image of the set containing U and V. And finally, we'll wrap up with the inverse image of the set containing X and Y. Okay? So does everybody remember how we find the image? When we have a subset of the domain, this is a subset of the domain A of G of F. The image of that subset is the set of second coordinates that these domain elements pair up with, right? Everybody remember that? So what is G of F of this set containing 1 and 2?
The set containing X.
And why is that?
Both numbers point to X on the image.
Yes, it's exactly because G of F of 1 is X and G of F of 2 is also X. So everything in this particular set, namely 1 and 2, both map to X. Does that make sense? So what's G of F of the set containing 3 and 4? Somebody else. I really appreciate your your participation, Edwin. If you didn't participate, sometimes I swear I feel like I'm talking to myself.
YZ.
YZ. And YZ is that?
3 matches to Y and 4 matches to Z.
That's exactly right. 3 maps to Y and 4 maps to Z. So you could say because G of F of 3 is Y and G of F of 4 is Z. Great. What about G of F inverse of the set containing U and V? I'll open the floor back up to anybody.
An empty set
It sure is. Why is it empty, Edwin?
because U and V don't have any pairs with A on the image.
Yeah, U and V do not have any pre-images in A. They don't pair with any elements from domain A, do they? Because no element in A pairs with U or V under G of F. Great. Last but not least, G of F inverse of the set containing X and Y.
The set containing 1, 2, 3, and 7.
Anybody else concur?
I agree with that.
1, 2, 3, and 7. Let's see why. Why are these the preimages of those? Well, it's because G of F of 1 is X. G of F of 2 is X. G of F of 3 is Y. And G of F of 7 is Y. And there are no other domain elements that map to X or Y. These are the ones. Any questions, folks? This is a good time to ask questions tonight. No? Okay, so the notes that will actually be posted will be something like this, where I just ask the question why on that last one. Okay. But it's enough information. I just didn't want to take the time and draw this in front of you, but you're going to see a WebAssign problem with pictures like this, at least one. It's good practice and it's very helpful to get a visual. All right, that is now going to be page 5 in the notes because I'm writing a little bit larger than I did earlier today. All right. Let's talk about the identity function on a set X. So the identity function is also called the diagonal function. Here's the definition. Given a non-empty set X, the identity on X denoted by, well, there are a couple of different standard notations. All right. F has decided to use capital I sub X. So that's one standard notation. But also, she used to use the more standard, kind of more advanced notation, which is the Greek iota. You know, the lowercase I in Greek is iota. It doesn't have a dot, by the way, in Greek, sub X. So either one of these is standard notation for the identity function. Is defined as follows. The identity function on X of an element little x is just that element little x for all little x in the set big X, okay? Give these feet, I can give big X feet so that we can distinguish it. So it's the function that is kind of like the mirror function. You know, you drop an element in and just out comes that same element. It's like the element looked in a mirror. So, you know, n drops an element little x from this set big X, which is both the domain and the codomain of the identity function on X. And out comes X, the same X. And clearly, the identity function on a set X maps from that set X back into that set X. Okay. In the reals, we haven't talked about a lot of infinite functions because I kind of like to keep it finite when we go through this discussion in chapter 7. Otherwise, we never get out of chapter 7. But one identity function that you're familiar with, I'm sure, is the identity function on the reals. It maps from the reals to the reals. You have, it has this graph. You've seen this graph. It's one of the first graphs you probably ever learn as a student. Everybody know what it looks like? It's the line, the straight line that makes a 45-degree angle with both axes. It's known as f of x equals x or y equals x. But in fact, it's the identity function on the reals of x equals x. So the reason it's called the diagonal function is if you look at the ordered pairs, they look like little x comma little x, where x is in the reals. And if you graphed, okay, yeah, it's a diagonal line. And if you have a finite set, it just becomes, these dots. They look like just dots along a diagonal. If it's in a grid configuration, it's even kind of more obvious. It can also apply to database theory. So have you seen the identity function before, folks? There's a reason why we care about it. And the reason why we care about it is because there's a property of functions that have functional inverses that's related to the identity function. So we want to talk about the functional inverse. Not every function has a functional inverse. We can always find a set theoretic, inverse, the inverse set. But that doesn't mean that g of f had an inverse function. This notation is used for both things. Inverse images, these are just sets. That doesn't mean, again, that function had a functional inverse. So I gave you a do later on Monday night. It was 4 questions, and it was quite important. Do you remember what that was? It was the last question from the notes on Monday, where I gave you a set X and I gave you a set Y. And you were asked, is it possible to build a function f from X to Y that's onto? If so, do it. If not, why not? Is it possible to build a function G from X to Y that's 1-to-1? If so, do it. If you can't, explain why not. And then I asked the questions, 2 more questions the other way. Is it possible to build a function h from y to x that's onto? If so, do it. If not, why not? Is it possible to build a function k from y back to x that's 1-to-1? If it's possible, do it. If it's not possible, why not? Did anybody take a look at that do later problem? I hope so.
I don't remember it.
You don't remember it. Well, there was a reason why I asked you to look at it, because there was a difference between those 2 sets. And here, let me see if I can find the notes. there was a critical difference between those two sets that made those answers, more interesting than they would have been. Here's day 22 notes. This is the last example that we discussed. Notice X has 5 elements and Y has 6 elements. So is it possible to construct a function from X to Y that is onto? Let's
No.
just look at that. Is that possible? I'm sorry, Edwin, you said something, but I didn't hear it.
Oh, no, it isn't onto it. Or it can't be.
It can't be. Why not?
Because X didn't have enough elements for Y.
Everybody see that? Every element of X is going to have exactly one arrow coming out of it. That's the definition of a function. Definition of a function basically says each domain element gets one arrow. Must have one arrow, can only have one arrow. Well, so there are going to be 5 arrows coming out of X. That's not enough arrows to cover up Y. So there's no way that a function from this X to this Y could be onto, because onto Y means Y gets covered up like a wall-to-wall carpet onto the floor. It would have to get covered with arrows. But there's 6 elements over here in Y. See what I mean? So there's not enough elements in X to do that job. Any questions? What about one-to-one? Is it possible to build a one-to-one function from this X to this Y? In other words, can the arrows from X get spread out so that no 2 elements of X have their arrow shoot the same element over here? That's what one-to-one means.
Yeah, it could be one-to-one.
Yeah, it could be, because we've got enough elements over here in Y that each element from the domain can have its own private partner over here that it doesn't share with a different element from X. So you review these definitions of one-to-one and onto, and then I ask the question the other way. Is it possible to construct a function going the other way from Y to X that's onto? Is it possible to construct a function from Y to X that's one-to-one? So now we're going back this way. Can we build a function from Y to X that's onto?
Yes.
Because there's enough elements in Y to have enough arrows to hit everything in here. Because there's more elements in Y. What about one-to-one? Can we build a one-to-one function from Y toward X?
No.
Kendall, are you following? Everybody following? So good. So what's really going on here? Why are the answers yes to some of these questions and no to some of these other questions? Anybody got an idea what's really going on? What's different about X and Y? What makes them different? Besides the fact that the symbols are different.
Y has one more element than X.
That's the critical difference here. Y has one more element than X. Okay, good. I'm glad we reviewed that, because now we need a definition of what it takes for a function to have an inverse, and then we have a theorem that tells us exactly when a function can have an inverse. Given a function f from X to Y, if there exists a function g from Y to X with the property that actually two properties. G of F is the identity on X, and F by way of G is the identity on Y, then G is the functional inverse of F. Or just the inverse of F. We use this notation. G is equal to F raised to the minus 1. And it maps from Y back into X. And the intuition behind the functional inverse, folks, is it just undoes whatever F did. It's kind of like the process of tying your shoe is the inverse of the process of untying your shoe. The process of opening a door is the inverse of closing the door. Okay? So here's a theorem that gives us a full characterization and tells us exactly when a function has a functional inverse. Theorem. A function f from x to y has a functional inverse if and only if so it's a full characterization. F is onto and F is 1-to-1. That's what it takes. Now, based on what we just reviewed from the day 23 example 7, if we want to build an example now of a function f from an x to a y, and we're going to want that function to have a functional inverse, what are we going to have to do about x and y? What's going to have to be true for x and y? If you believe this theorem, I'm not proving this theorem, but I'm going to maybe do a proof by picture if we have a little extra time.
That they have to have the same number of elements?
That's exactly right, Nick. That's the bottom line. For a function from x to y to be onto, x has to have at least as many elements as y. For a function from x to y to be 1-to-1, y has to have at least as many elements as x. So it's the old x is less than or equal to y is less than or equal to x. That forces them to actually have the same size. So let's put 1, 2, 3, and 4 in x. And in y, let's put little a, little b, little c, and little d. We don't need to do a huge one here. We're just going to do this last example. Consider this function, f from x to y. Just to make things a little different, I'm going to send 1 to d, 2 to c, 3 to b, and 4 to a, just to mix things up a little bit. So let's just notice a couple of things. F is onto. Why? Can you write a sentence to explain why it's on to? Should practice doing that. Because on the test, you're going to have to write, a few short sentences. F is 1-to-1. In other words, are you familiar enough with these definitions that you can explain why a given ordered pair set is a 1-to-1 or onto function? Now let's find F inverse from Y to X. It just undoes what F does. Super easy. Super, super easy. It just undoes what F does. And so if 1 got sent to D, then D goes back to 1. Right? 2 got sent to C, then the inverse has to send C back to 2. So I'm going to start with A because we're mapping out of Y, and I'm going to write them in alphabetical order by domain element. So A maps back to 4. B maps back to 3. C maps back to 2. And D maps back to 1. Okay, you check later. That F of F inverse is the identity and F inverse of F is the identity. But I'm going to ask you this now. Which identity? Which identity? One of these compositions is going to be the identity on X. One of these compositions is going to be the identity on Y. Which one is which? Well, let's just think about it. F of F inverse. Which function is acting first?
Y
I'm
or what?
sorry, Y is not a function.
F or negative inverse of F.
Yeah, F inverse is acting first. So when we think about this function, F of F inverse acts first, right? So you're right. Out of Y, F inverse acts first. And then sends elements to X. And then F acts second. And sends those images to Y. So this is the identity on Y. Whereas, see, a picture can help. Whereas F inverse by way of F, well, it's by way of F. It means F is acting first. So it maps from X to Y, and then F inverse happens next. So that's the identity on X. So you can check that these compositions, I mean, it's easy. 1 goes to D, D goes back to 1. So 1 goes to 1. 2 goes to C, C goes back to 2. So 2 goes to 2. Blah, 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 blah. Okay. And so on and so forth. That would be F inverse by way of F, because I was doing F first. So that would be checking this one. Okay. Are there any questions? a student in an earlier class did ask a question about one of the homework problems, about the summation formula. And I'm going to sit down tonight and grade those papers for you, and I'll get those done. Oh gosh, I've got an office hour tonight from 8 to 9. Darn it. Well, I'll do it. It's the next thing on my list. Okay. Once I get what I have to do done as far as office hours, emails, that sort of thing, I'll get that graded. There aren't that many of you. It doesn't take that long to grade your papers and get that uploaded for you. And then I'll be grading the homework that you just turned in, homework 10, over the weekend. And you'll get it as soon as it's top priority, folks. I'm definitely going to try to get those to you very soon. You've never waited more than a week to get something back from me, and I apologize. It's just been super, super crazy busy. So I'll just post this extra page of notes about just kind of a little bit more about that summation formula. So you've got plenty of good stuff to work on. You can review if for some reason you felt like you didn't really spend as much time as you needed to on those special homeworks, 9 and 10, or you got back 8 and you weren't that happy with it. Rework those problems. Come to office hours. We can talk about whatever. If you haven't, I haven't even started grading homework 10 yet. I noticed somebody just submitted it. I'll accept it. Just go ahead and submit it. The most important thing now is that you do these, right? And get them to me by tomorrow at the latest if you can. Email me if you need to. All right. It's just real important that you do those. Any questions? I'll let you go. I don't want to keep you here longer than you want to be in my company. Much as I enjoy your company, I don't want to make you feel like you've got to stay. Okay. See you soon. Don't forget your web assign. Skip around
Those are
here.
good. When are the day 22 notes going to be posted?
They aren't, they're not up?
No.
What?
The latest one is day 21.
What? Hang on. Why didn't you email me?
Uh,
I
well,
sure wish you'd emailed me and told me that.
I think
Maybe you just didn't look for them, huh? Until just now?
yeah. And
I
Danny
got
was asking in chat.
I think I
what?
sent an email out earlier
What?
today.
Speak up.
I think I sent an email out to you earlier today about it, or
You did?
yesterday.
Like
Yeah,
right before class?
not right before class. I think it was maybe this morning or yesterday.
What? Seriously? Day
Also, do you
22
know when
notes?
the day 22 video will be put up?
It's up. What's going on? What the hell?
Yeah, the YouTube video isn't up either for 22.
Okay, I see that I did not post the day 22 notes, but I definitely loaded did you scroll down in the YouTube channel? Because even though I've got it, hello, are you there?
Yeah.
Even though I've got it set that the newest is supposed to post first, it keeps sticking them down at the bottom. Day 20, day 22 videos up. The day 22 videos there. What's going on? Let me check this privacy settings, because something happened before where it was, no, it's up, it's public. It says file name is day 21. What? Wait a minute. But it says day 22.
Okay, so you got the announcements about the test next Monday.
What's going on with this video?
We didn't get further in chapter.
It's here, day 22, section 7.1 to 7.2, my video. What is going on? Let me look at the details. This is the details. It's in the fall lectures. Settings.
I mean, for the lecture playlist, it says there's one unavailable video that's hidden.
Yeah, I was just about to say that. And it does say updated yesterday.
So what the hell's going on? Listen, I try to do this. It's in draft state. Oh, okay. It says it's in draft state. Why does it do that to me? It's like I'm so sorry. I'm so frustrated because they changed YouTube, and I used to be able to just load it up and walk away, and I didn't have to do anything else. Listen, so you said you emailed me?
I did, yes.
Nick, you emailed me.
I emailed you 8 o'clock. Where am I?
I'm checking my email right now because I sure did. I'm going to look for it because that's like a double failure, and I hate for stuff like that to happen. A double failure, October 22nd, day 22 notes are not up on Blackboard. So, and I said, thank you. I didn't reply. Okay, so you said the notes, but you didn't say anything about the video, but I did not somehow, I guess it was just really busy. It's been really busy. It's been ridiculous.
Well, it's okay. I understand. It's fine.
I really, it makes me upset because I don't like to have a fail. Anyway, it's up now. Thank you so much. Because you need that, right? Thank you so much. And if it ever happens again, somebody, might even the next morning go ahead and, well, that's what you did, Nick, and I didn't see it. Darn it. You can message me through, I always see my emails. I say I always see my emails. What was going on that yesterday I didn't see the email? Yeah, it was first thing in the morning. I guess I just got buried in other stuff by the time the day started. I'm so sorry. Anyway, so I will have to just double check and make sure the video goes up tonight. Like I said, it doesn't seem like I can just walk away and go to bed anymore. I have to wait for it to process. And then, I don't know, YouTube is changing. Does anybody else have a YouTube channel? Yeah, yeah, they've changed things. And it used to be just so easy. I just drag it in there, put a few little things, next, click, and I could just go to bed. But this is the second or third time this semester this has happened. So I don't like that. It's like they're checking it for something, like something they didn't used to check it for, and it's not made for kids, so it's not like that, but like checking it for accessibility, or maybe they're doing some kind of content check. I don't know. Anyway, maybe they've changed their screening. It's weird. So, are y'all hanging out for the office hours?
Uh, oh, I'm about to run. I was gonna say have a good rest of your night.
Hey, you too. Thanks for letting me know. And I'll get your stuff graded ASAP.
All right, thank you.
You're
I'll see you
welcome.
Monday.
See you Monday.
I'm gonna go also. Have a great rest of your night.
Hey, Nick, you're all set to take the test on Monday.
Thank you.
Okay, don't forget your calculator.
All
Okay,
right. Thank you. Have a good one.
you too. Hey, Danny.
Hello. All right. See you, Professor.
See you. And thanks for your help.
Yeah.
Appreciate it. Have a good night.